Hello, everyone, and welcome to our discussion. In this discussion, we are going to talk about the designing of the professional engineering requirement using the IEEE 1233 standard. Uh, this workshop is not going to be about the theory or vocabulary. Is actually is we are going to discuss about the tool that would help us to write the engineering requirement. Uh, why we need that? Because we need to build a testable, certifiable kind of like technology. And our goal is that by the end of this discussion, you'll know exactly how to move from the stakeholders' needs to a testable requirement. And actually, that process is where the real engineering begins. But let's begin with a question. What what do the most of the engineering failures, system failures have in common? It's not about that engineers were not smart enough. It's not about that the technology wasn't available. It's basically somewhere, the reason is somewhere during the process, someone assumed something that wasn't right. Okay? That standard IEEE 1233 is basically exists to define a function, describe a behavior, or constrain a system, okay, uh, and implement, test, and even legally certify that technology. If your requirements are vague or incomplete or actually like are unverifiable, then the best design still will fail to meet the expectations. Let's move on to more in-depth discussion about this standard. Now, why requirements drive engineering success? First and foremost, when we are going to do a project, we basically are designing a solution to align with the stakeholder needs. So the requirement that we need to create for that certain engineering design create a common understanding between the technical teams, management, and the stakeholder or what we know and client about what will be developed. Okay. The cost and the schedule predictability is actually defined, okay, based on the requirement. That requirements actually allow us to accurately estimate the resources and the time that we need uh, for implementation of that design and finalizing the project. Every project that we do, we have to verify that the result is actually meets the expectation that we define. Okay, so the solution that we're providing for the stakeholders, for the clients, needs to be consistent with the expectation of defined the expectations defined by those stakeholders. Okay, so therefore we need to test our result. We need to verify and validate that we meet those needs. These requirements actually are the base of how we could define the process of testing, okay, and how we have to validate the result. And if we define the requirement clearly, okay, basically we could identify the possible issues, okay? And when we have those and when everything is clear, basically it would reduce the risk during the process. Now, IEEE 1233 is a thinking framework. It's not just a standard. Okay? When you define the requirement, okay, you actually structure the technical specification. Okay? Meaning you have a professional documentation. We are ensuring by doing that, we are ensuring that the requirements, okay, are testable. So when we clearly define the requirement, we make sure that all those requirements are testable and we can validate the uh, 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 the quality of our result. This requirement that we develop for any of our project, okay, or any of our design is basically is it will translate what the expectation and needs the stakeholder has, okay, into the engineering language, so the engineering team could provide a solution perfectly matched with the needs that basically cause that project to exist. Okay. And when we define those requirements, now we have a basis for stakeholders to be able to understand clearly what they're going to get and what would be actually the level of quality in the end result, in the deliverable result. Now, in this discussion, we are going to recognize some flawed requirements, okay, and basically learn first of all to identify the pitfalls. Okay, so you already uh, uh, probably gonna read some uh, uh, documents about a certain project, either as like an engineer or a red team kind of like testing facility, or even you are a stakeholders for that. So you are the client, you are gonna receive the result. Uh, by learning how to identify those problems and those flaws, you can basically find the weaknesses in the requirement. Ergo, you can fix those weaknesses and address those issues. Then we are gonna analyze the structure and traceability that we need to have in those requirements, so we could connect actually the stakeholders' expectation to system verification and make sure that we cover everything completely and comprehensively. After that, we learn how to write. We are going to discuss how to write the professional grade requirements. Okay, so we could develop that requirements document. Okay, which are clear, feasible, they are not ambiguous, and they actually cover everything. They are completely cover every aspect of that project. And in the end, we are going to align it with real world constraints, because some of the requirement that we made, we do that, we develop them based on the theory. But we all know from the engineering perspective that the theory and real world execution of those requirement has a certain level of like a difference. There's an error in that. So we can perfectly see what we have in theory in real world. So we have to align that with the constraint that we have in a real world implementation of that requirement. Now, let's talk about some of the failures that actually happened, okay, engineering failures that happened in real world. Okay, case one, the Challenger disaster. Okay, the shuttle exploded in 1986 due to an O-ring seal failure at low temperature. Why that happened? Because no requirement ever explicitly stated that that seal must operate reliably at freezing temperature. What was the result? The catastrophic loss of seven lives. Those astronauts, okay, are lost their lives because of the simple uh, requirements that were missed during the defining period of that project. Another example is the Denver Airport baggage system. Okay, that system was fully automated, futuristic, and but fully dysfunctional. Why? Each vendor delivered their component without a shared requirement of how subsystems could communicate with each other. Okay, that missing system level requirement basically destroyed the entire project. Those subsystems did not communicate properly, did not work with each other. Ergo, the global system, the general system, failed entirely. Although that was a brilliant design put into each of those subsystems. That was a multi-million dollar lost, actually, that project. Another case, we had a healthcare.gov platform that crashed. Okay, because there was no agreed upon baseline, constant requirement changes, the team built components that could not integrate. The system failed nationwide, live in front of millions. Okay, and these aren't just the edge cases. These are the example from aerospace, infrastructure, or national IT. Their common thread is bad or missing requirement. Now, the key lesson from those cases is that the requirement as a system are the system foundations. System killers are actually the poor or missing a requirement. Is not a minor problem or mistake. Okay, it could have failures that leads to the financial impact, or more importantly, those lives that, like for example, were lost in that aerospace challenge of failure. Okay, unclear requirement could cause an unpredictable and will cause actually unpredictable delays and problems. Now, what is the IEEE 12 33? So what do we do to prevent that by using IEEE 1233? The IEEE 1233 is actually a formal guide. It's not just a checklist, it's a formal guide for writing system requirements specification. Okay, so it helps you to answer 5 basic questions with the precision. Okay, the first question, what exactly must this system do? Second question, under what conditions the system will do the expected, will meet the expectation. Third question is to what level of performance the system will meet the expectations. Fourth question, how will we know that we did a great job and it's done correctly? The testability, the verification. Okay, and question number 5 is how does every requirement that we put into that project trace back to the stakeholders' expectation or the objectives of the project? Now, the IEEE 1233 is not just for electrical engineering, it's used across industries okay? Especially where the reliability and certification matters, okay? It could be the power system, it could be defense, aviation, healthcare, or transportation. And it aligns directly with other major standards. Could be like IEEE 830 for software. It could be ISO 29148 for systems lifecycle, or ISO 15288 for like V model development. So how do we actually define a good requirement? IEEE 1233 says that every requirement must meet several kind of like quality or like properties. The first one is the necessary. Okay, that necessary means it reflects that a real stakeholder's need are met. It's not just a, a fluff into the document. Okay, it should be verifiable, those requirements. So we can prove it's done using either the inspection, test, or analysis. Okay, those requirements should be feasible. That means it can be implemented with current technology. It's not just a dream. Okay, we can do that with current technology, with budget that we have, and with the resources that we that are available for us. Okay, the feasibility is the third characteristics of a good requirement. Okay, the next characteristic is unambiguity. There is only one way to read it. Okay, the requirement should have the structure that there is no interpretation. It's not possible for different teams or different engineers to understand differently from that requirement. So there is only one way to, should be the only one way to read that requirement. So it should be extremely precise. Okay. And it should be complete. The next characteristic should be complete. So it should fully defines a single function or a constraint. Now, uh, uh, let me give you a quick example of a poor versus professional requirement. We could say the interface shall be user-friendly. Okay, that's a very poor requirement for an engineering project because everyone, is ambiguous. You can verify it, you can test it because there is no parameter, there is no quantity in it. Okay, and it's incomplete because it doesn't define the task, it doesn't define the user, and it doesn't define even the actions. Okay, how we could enhance that? The professional requirement reading should be like the system is that this that statement. The system shall allow the user with no prior training, okay, to complete power routing configuration within 3 minutes using no more than 4 interaction steps, with task completion success rate exceeding 90% as verified by usability testing. So everything is now clear. We know what are the actions, we know how to test it, we know what are the criteria of verifications, and there is no ambiguity in it. So everyone knows what to do. Okay, everyone knows what is the expectations. Okay, now in this professional requirement, the strengths are they are measurable. So we have time, steps, and success rate quantified. So they are measurable. They are user specific. So defines the user profile in this specimen. So it's not just vague description, and it has a clear test criteria. So the objective of a validation or evaluation is completely clear. Now, The IEEE 1233 structure, okay, is basically upon three pillars. Okay, one is the boundary definition. Okay, uh, the boundary definition uh, is actually a system contains a diagram, okay, that defines the boundary between the system of interest, those expectations that the stakeholder has, and its external environment. Okay, what is the condition that that system could work on, and it prevents that scope creep by clarification and basically defines the out of scope for the project. It also interface identification. It has interface identification. What is the format, timing, and security of the communication? Okay. It defines that like all external entities and visualize the input-output flows. Okay, so ensures that interaction are accounted for every requirement. Next step is the example elements. Okay, a typical diagram might include elements like DER, controller, utility data aggregator, energy management system, all that. So it might bring some examples for clarification of how the requirement actually defined. Now, let's talk about the requirement categories. Okay, there could be several different type of requirement that we need to develop for a specific project based on the IEEE 1233. The first category is the functional requirement. Okay, the functional requirement is actually what does the system do? Okay, and under what conditions? So basically, we define the deliverable and the scope of the project. And we define, okay, under what conditions actually this project could deliver the expectations. For example, the system shall automatically disconnect the DER, distributed energy resources unit, within 500 milliseconds of detecting reverse power flow exceeding 2 kilowatts. So the function is defined and is precisely defined, and the condition of that specific delivery also is defined in that statement. Next category is the performance requirement. So basically, it tells us that how fast or how accurate or how reliable that system works. For example, we could say like the interface shall refresh telemetry displays every 1 second with no more than a 250 millisecond delay from field data update. Okay, so we define the quality of the performance of our system. Okay, the next category is the interface. In interface, we define the format, timing, and the security of the communication between the subsystems. Okay, so we define the communication, and that subsystem include the external kind of like communications or interactions. For example, we could say one of the example of this kind of like in this category of the requirement is that the system shall publish DER dispatch commands using a certain amount, like this in this case MQTT protocol over TLS 1.2 encrypted sessions with authentication by X59 certificates. So you see how precise the requirement is. So it exactly defines the protocols and the condition of the communication between the system, between the interface, between the control system, and between the actuator, the whole subsystems. Okay. Next category is the constraints requirement. The constraint requirements answer to the question that what external rules or limitation applies to our system, to our design. Okay. For example, we could say that the system shall maintain functionality when subjected to the ambient temperature ranging from 40 Celsius to 40 degrees Celsius to 60 degrees Celsius and up to 85% relative humidity. So we are defining a condition to show that, okay, our design would meet the expectation based on all the previous requirement that we defined if the ambient condition is what we define in the constraint requirement. Now, how to write a high quality requirement? That's actually one of the basic discussion that we are going to have. Okay. If you take nothing else away from this session, take this. A requirement is not a wish, a feature, or a vague goal. It should be precise, testable statement. I am emphasizing that. It should be testable and phase statement about what the system must do and under what condition the system has to do that. And what is the performance expected from the system while doing that objective. Okay? Every requirement must be first atomic. What that means? That means only one behavior per sentence. So we do not write a requirement for several aspects of our project or our design or our solution. So every behavior, every objective should have their specific requirement statement. Okay. Next characteristic should be active. So there is no passive voice. The system shall blah 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 shall do something, shall meet this expectation, shall be following this criteria. You know what I'm saying? So the system will work under this condition. Okay. Next thing to have a high quality requirement is the contextual characteristics. When does this requirement apply? Okay, so it's not just any requirement would be applied at any condition and any time. Okay, that's not that's actually a dream. What we said is the requirement should not be a wish. Okay, it should be feasible. It should be realistic. So conditions would affect the project or the object or the performance of our design. So we have to make sure to mention when does that specific requirement apply. Okay, then the next characteristic it should be the requirement should be measurable. That's actually emphasizing. I put already emphasized that the testable statement, the testability of the requirement, okay, basically mandate us to have a measurable quantity for those or quantities for those requirements. So what number or limit proves that we met the expectation? We met our atomic active contextual requirement that we wrote. So we could validate our work, our solution. A bad example would be the battery shall operate reliably in all environment. What's wrong? First, reliably is undefined. How you could test that is reliable, that this system is reliable? What is the criteria of accepting and rejecting the reliability? Okay, all environment, the phrase all environment is that wishful thinking, is the dream requirement. It's impossible. We have to specify in what condition the system, the solution can be reliable. Okay. And how do we test that? It's not just the criteria, it's the process of testing. Okay, like the criteria of reliability is like certain parameter, but how we test that parameter, what is the process, what is the condition of testing, what is the error accepted on testing to meet if the solution is accepting is going to be accepted as a verified kind of like a solution, or it could be rejected that doesn't meet expectation of the client or stakeholders. Now, if we wanted to like revise that statement, we could say the battery subsystems shall deliver 24-volt plus and minus 5%. So now we have a criteria for reliability at the ambient temperature between minus 20 degrees Celsius and plus 60 degrees Celsius, and humidity up to 90%. So now we know when we should expect, under what condition we should expect that system to meet that reliability criteria. Okay, and it should be non-condensing. So now we actually made a requirement that has a boundary condition, has a unit, has a tolerance, and it's actually testable. Now, the key terms and modal verbs in IEEE 1230 that you should kind of like pay attention to, okay, is important because these terms shall, should, may, and will in the standards have a specific meaning that if you change those words, it's actually change everything. The requirement is changed. Now let's talk about that. The word shall is the strict, the more strict, the most strict kind of like word. When you use shall in the statement, that means that a specific requirement is mandatory. So if the system does not meet that requirement, it's failed. It's not accepted. Okay, so normally it's used for critical functionality. Okay, the word should has a it's actually used for a requirement that are recommended, not mandatory. They are recommended, but they are not required. Okay, they normally use when there is a flexibility. Okay, is needed, but the preference is clear. The word may, okay, will be used in the requirement that are optional. So you can take it or you can ignore it in your solution. So they are good for features and they would add values, those requirements that you use the word may in it. They would add values, but they are not mandatory. And even they are not recommended. It's your choice to meet them or not. Okay. The word will is actually descriptive. So it's normally used for project planning, not system behavior. Okay, it describes design facts or planned actions. Let's go for some examples. Like for the shall, we say the display shall refresh every 1 second. So it's a mandation. there is no flexibility on this condition in this requirement. The next example, the interface should allow custom layouts. Okay, this is a recommendation, is not a mandatory requirement. The battery may support hot swapping. This is a suggestion. You can take it, add value to your project, or ignore it. Next example is the supplier will deliver unit logs monthly. It is not a requirement, it's just an action plan. It describes the supplier's kind of like action plan. These words actually carry legal and engineering weight. So if you don't pay attention to these words, there is a big responsibility tied to them. They are legally have weight on the project. Now, we have to basically avoid the ambiguity when we define the requirement. What did I mean by that ambiguity? Okay. Engineering disaster don't start with wires or codes. They start with vague word or terminology. Like subjective terms as fast, safe, reliable, easy, robust, appropriate, adequate. They are vague. Everyone can have their own understanding of how those word means. Okay, and they are dangerous. They are dangerous because everyone reads them differently. Instead of safe, we could say like the output shall not exceed 60-volt DC under any failure mode. So now we have a requirement mandated, it shall mandated, and it has a quantity that you could measure if based on that quantity if the system is safe or not, and it defines the condition. So that system, even if it's in a failure mode, shall meet that requirement. Instead of fast, simply say the system should be fast, we could say, like, for example, the controller shall execute step points commands within 200 milliseconds. So now we have a testable quantity that defines specifically what we mean by fast. And it's not like everyone could have their own understanding. It's very specific and it's shall, so it's mandated. Okay, so pay attention. Precision is not a nitpicking. It's actually the engineering integrity. Now, when we wanted to like have a writing the requirement, there is a guideline for that. Okay, the first step, the first characteristic, we already mentioned that once. We have to use active voice. Okay, so the system shall detect overvoltage. Overvoltage. Okay, the bad example is overvoltage shall be detected by the system. That's not active word. The active voice. Okay, the proper one is the system shall detect overvoltage. We have to avoid compound statements. Every requirement, every sentence, a statement that you use for describing a requirement should only, actually, let's use shall only state one function or one condition or one constraint. Okay. We have to include the thresholds, the criteria, what we mean, how we could quantify that requirement so we could test it and decide if it's fail or pass. So we should have a specify the environmental condition, interface references, etc. when they are applicable. We have to use the structure requirement IDs, the format like REQ 001 or IFAC 020 or PRF 110. If you format those requirements, structure those requirements like that, okay, basically you make the document capable of traceability and requirement management. Now, there are always supporting standards and basically definitions. We have IEEE 100 that basically defines all the terms precisely. Okay. We have IEEE, for example, 830 that reference for detailed software requirement. Okay. Or ISO IEC 29148 that is utilized it is utilized for system lifecycle requirement. Okay, they are like these standards could be supporting standards for 1233 for you to actually develop those requirements. You could reference those, you could use those supportive standards in addition to the 1233. So you could have precise professional requirement for your project. Now, formatting of the professional specifications is very important. How to do that? You have to begin each requirement on a new line. It's not a haphazard text. We have to have clarity, separation between distinct requirements. The prefix with unique identifier, what that means. When you start the requirement, when you code the requirement with a specific prefix, you make that precise requirement coded so you could reference that later on or actually trace it, track it through the whole document. You have to group them by category. It's not just coding them. You have to group them by category. Some of the requirements, as we discussed, are defining functions, how functional the solution is. Some of them are about the performance and the level of the quality of the deliverable. Some is about safety. Some is about the regulatory. So you need to categorize them, not just haphazardly put every requirement into documents. Okay, so it would be easily found and traceable. We have to maintain a cross-reference. So if we have figures, we have to link it. If we have a table, we have to link it. If we have external, we use the external standards, we have to cite it. Okay, so it has to have a cross-reference for clarification. That's help us for clarification and be more precise. So if beside all those, after all those specific description of the requirement, if someone has a question or someone has like a misunderstanding or there is not clear enough for someone, they could use that cross-reference to clear up that confusion. We have to have a track version stories. So some documents actually change requirement. Like you probably work with the standards. Every standard that you read, it has several versions. Okay, and you have to follow the last version when you're designing a system based on that standard or based on that document, not just standards. There should be a regulatory kind of like guidelines. So those documents should have a track version histories. So everyone knows what was the previous histories and what is the change made from the previous version to the current version. Now, best practice for writing requirement, again, active voice. We have to be quantifiable and verifiable. Okay, so it has to have, every requirement has to have a quantity that you could test. We have to have one requirement per statement. We do not mix requirements with each other. And we have to include the environmental or constraint that we have because we need to be realistic. It is not a wish, it's a requirement that we have to meet. Now, how we could validate? Now we write the requirement, how we could validate that we did a good job. First of all, we have to review that, conduct a formal, if possible, peer reviews, okay, that make sure that there is a clarity, it's complete, and it's feasible with a specific domain experts, testers, and project stakeholders. Okay, it should be traceability matrix. So when you're reviewing your requirement, you have to ensure that every requirement maps to a stakeholder's expectation or the objective of the project. And all the subsystems or components are traceable with each other. So they are mapped, they are connected with each other. They meet each other in the requirement, in the general documents. And all the test methods are compatible, consistent with each other. Okay, so we don't define a certain requirement for one subsystem and different requirement for another subsystem, which make contradiction when these two subsystems connect to each other and try to work with each other. We have to control the changes. As we said, the versions of our document should be traceable. So we have to have history. So we could easily find how the current version is modified and changed in compared to the previous version. Okay. We have to develop models and prototypes. Okay. So we could feasibly validate and we could validate the feasibility and the test assumptions and the tools that we design for that requirement, okay, using simulations or prototypes, experimental lab prototypes. Now, there are several like requirement management tools that you can use. One is like, for example, the uh, IBM Doors Next Generation is a baseline control, cross-project linking, and robust. It provides those a robust traceability. The JAMA content is actually a very good agile requirement workflow, okay, that connect the engineering team with the stakeholders, okay, or Plarian ALM, which actually integrate life cycle management and is consistent with the ISO 26262. So there are several digital tools that could help you manage the complexity when you talking about the larger scale project and could support the hierarchy of organization within the requirement. Now, how we could conf uh, apply a configuration and a version management into our system. First of all, as we said, we have to have a unique identification. Each requirement must be coded uniquely. We have to have a control documentation. So requirements belong to control documentation revisions. Okay. And uh, all the requirements should reflect the current system design version. So not previous versions, the current versions. Let's talk about some examples, some case studies that we could go through to clarify what we're talking about. One is like the smart grid controller. Uh, Imagine a university spin-off company that is developing a smart grid controller. This system coordinates the distributed energy resources, detect the outages or islanding events, and sends dispatch commands to the inverters and battery systems. Okay, so what would happen? The expectation is that it should react fast, communicate securely, okay, operate reliably under harsh environment, and meet both utility and regulatory requirement. Now, let's how we could professionally set the requirement for this system. Uh, let's give an example. We could develop, like for example, a performance requirement. Okay, number one, we code that requirement. Like for example, here I used like SG smart grid REQ requirement 001. So I code that requirement. This is like optional. You could code that based on your own interest. Okay, so this is not like you have to use the acronym. Okay, it's only the requirement is that to every requirement the only condition is that every requirement should have their own specific code. Okay, now for the performance, we could one of the requirements should be this example. The controller so it's mandated, shall detect a frequency deviation bigger than zero point 0.2 hertz from nominal value, which is for this example is 60 hertz, okay, within 100 millisecond. So we define the requirement, we define how fast we want, okay, to detect that, and issue corrective step points to all connected DERs within an additional 150 millisecond. So we precisely defined how this system should perform if, for example, there is a frequency deviation, in the case of frequency deviation. Okay, and because it's fully quantified, okay, and we have a quantitative description, we can test this requirement. We could test our solution to see if it meets the requirement, and we can analyze it to verify that that our solution meets that specific requirement. Next example, SGREQ002. So you see, the codes are different. So like, if you want to reference that or trace that, we could easily trace that. The controller shall exchange DER control and telemetry data using IEEE 2030 Part 5 protocol over TCP/IP on port 443 with X.509 certificate-based authentication and TLS 1.2 encryption. So you see, this is like a requirement for interface, how these systems should communicate with each other. Okay, and it's precisely define the method for the communication between the control and telemetry data. And it's also referenced to another standards, which is going to be the supportive standards for these specific requirements. And we could verify that by the demo or inspection to see if our solution meets this requirement. Next example, SGRQ003. The system shall initiate autonomous islanding within 1 second upon grid failure detection, verified by the absence of utility voltage on all phases for more than 500 milliseconds. It's a functional requirement, and it describes how and when and under what condition our system should decide to go from the grid tied to islanding mode. And it defines how fast it should do. It's quantified so we can test it. That is the system actually meet that functions or not, properly apply that function or not. Now, there are additional samples that we could talk about. Like, for example, I'm going to review one of them. You can read the others. Let's talk about the SGREQ 005. It says the system shall operate continuously between minus 300 degrees Celsius and plus 30 degrees Celsius and plus 60 degrees Celsius at up to 90% relative humidity. Okay, non-condensing. It's a constraint requirement. So it's an environmental constraint. And we could verify it that the system would actually work in this condition. Okay, continuously by the lab testing. So you see every requirement has units, has boundaries, has actions, has conditions, and it's testable. Now, what is the rationale? Why we have to write like this? The reason is that because real systems get tested by real regulators, and the ambiguous language would not pass the review. You're not writing this for your own team. You're writing this for safety inspectors, for legal compliances, and future maintenance, actually. Okay, if you write poorly, it would cost time, money, and trust. Precise requirements save lives, reduce the liability, and protect actually your reputation as a professional engineer. Now, if you can define precisely, you can design it professionally. That's actually what IEEE 1233 teaches. And that's what you learn based on this discussion. So all the requirement encode user expectations. To sum up, encode user expectations, designer assumption, and regulatory guarantees to each other. Okay? Those requirements enables coordination between electrical, mechanical, and software engineers, or every other teams that are involved in that project. It will mitigate the risk by precise requirement for mitigating or reducing the hidden hazard, misalignment, or even legal and financial risks. Okay, so ambiguity is not lack of knowledge, is actually lack of commitment to clarity. This is what basically is the end kind of like message of the standard IEEE 1233. Thank you for your attention. Please let me know if you have any question, and have a good day.